Hello everyone. I have a couple videos here about factoring polynomials, and start out with a few main points for polynomials, and then we'll get to the factoring. Mainly in this video we're going to talk about greatest common factor factoring for polynomials. Alright, but they're important because they're kind of the building blocks of a lot of objects in mathematics. We can actually compute with them. That is, if I wanted to take a number and plug it into a polynomial and write it out on paper, we could evaluate. All right, and that's part of actually that polynomial homework, because a polynomial is just a string of terms where we have numbers times x or whatever variable raised to a power. Again, we can work these things out by hand. We don't do it a ton, but again, they're building blocks for more complicated math objects. To multiply out polynomials, we're going to use the distributive property. All right, so if we have a quantity times a sum, we know the distributive property tells us to multiply we can multiply each term on the inside by the factor on the outside and then add the results. Okay, so when we multiply out two polynomials, as we've seen before, we multiply each term in the first polynomial by each term in the other polynomials and then add the results. All right, and this is generalized to more than multiplying out two polynomials as well. One just quick note in terms of foiling or multiplying out two binomials, that's just an acronym. It's not really a property. We kind of use that acronym, which stands for first, outer, inner, and last, quite often. But again, it's not really a property. The distributive property is really what we're using there. There are some special product rules for multiplying out polynomials. We'll start to recognize those patterns, and they're going to help us for factoring in certain cases, not all. Alright, now factoring is really the reverse of multiplication. Alright, so let's just think about a number example here. So if we start with the integer 28, we can factor that as 7 times 4. So we're taking the number 28 and writing it as a product of smaller numbers, which we refer to as the factors, 7 and 4. Factoring polynomials is really just a generalization of factoring integers. We're trying to express the polynomial as a product of smaller ones. In this case, what we're meaning is polynomials of smaller degree. Alright, now we're going to be spending a lot of this section dealing with factoring trinomials. Alright, and we'll get to that in another video. There are some special factoring formulas also. We don't have to memorize them, but some of them will come up over and over again. In particular, the difference of squares formula, which might be worth memorizing. All right, but the processes for factoring trinomials and in general for polynomials is what's important. All right, and just a quick note that I don't have written on the screen here. In general, polynomial factoring is a very, very difficult thing. We're going to be doing it in cases that we can handle. If somebody just wrote down a generic polynomial, just making up numbers, it would be extremely difficult to factor it. All right. Now, that being said, for some basic polynomials, we can factor them. We're going to start out by talking about how to remove a common factor, which we're going to refer to as the greatest common factor. And whenever we can, we want to first take out the greatest common factor and then factor the resulting polynomial further if possible. Again, what we're doing here really is reversing the distributive property. Okay, so let's do a couple examples with this, and then I think in the next video we'll talk about factoring basic trinomials. Alright, so what we want to do for these is, just to get used to it, factor each term completely out. So for instance, the 4x squared term, we're going to write that as 2 times 2, because 4 is 2 times 2, and then times x times x. And then 20 we can write out as 4 times 5, but 4 is equal to 2 times 2, so we'd have 2 times 2 times 5, and then times x. And then let's just underline what is common between, as far as factors, in each term. Alright, so let's remember we have two terms in this situation separated by the plus sign, and we can see in each term we have multiple factors. Alright, we've got two factors of 2 in each term. We have one factor of x in each term. So for this first example, the greatest common factor, which we're going to denote by GCF, is going to be 4, which is 2 times 2, times x. Alright, so it's just 4x. Alright, again, you might be able to look at that and kind of decipher it without writing it out that way, but writing it out that way is kind of nice because when we go to now factor it, it tells us what we're taking out and what's left over. All right, so when we take out the 4x, we factor out the 4x. All that's left over is what we didn't underline before in red, and in this case that comes out to x plus 5. Okay, and we can check our work. That's one good thing about factoring. We can check our work by multiplying it back out. So if we redistribute the 4x through the parentheses, we would get 4x squared plus 20. All right, we're going to do a few more in this video with just basic factoring out of GCF. All right, so let's take a look at the next example we've got listed. All right, again, we're going to factor that as best we can. Now with this one, we've got 5x to the 6th power. Now, x to the 6th power we can write down as x times x 6 times. All right, a little tedious to write this out, but let's just do it this way for the first couple example. 30 we know is equal to 5 times 6, and then we've got x to the 3rd power, which means x times x times x. And then let's just underline our common factors. We've got a factor of 5, that's the common numerical factor. We only have 3 factors of x in the second term, and therefore we can match that up with 3 factors of x in the first term. All right, now again, we're going to take out our greatest common factor. So for this one, our GCF, write that off to the side, is going to be what, 5 and then times 3x's, which is 5x to the 3rd power. So we can factor out 5x cubed, and we're left with whatever we didn't underline, which is going to be in this case x cubed minus 6. All right, we can double check that by multiplying it back out. All right, let's look at a couple more of these examples, and then we're going to stop with this one. And we can do this for for polynomials that have more than 2 terms. Let's skip the next one and go down to this one where we have 5x to the 9th plus 70x to the 6th minus 45x squared. I'm going to do this one a little bit quicker. Instead of factoring it out in terms of x times x in each term, let's look at the smallest number of x's we have. And for this problem, the smallest power of x is x squared. So let's think about how can we rewrite each term as something times x squared. All right, so the first term we've got is 5, and then it's going to be x squared times something. Well, x squared means 2x's, and we had 9 because we have x to the 9th, so it's going to be x to the 7th power plus now 70. How many times does 5 go into 70? If you need to, get a calculator out and do that division. All right, do 70 divided by 5, and you'll see it's 14. So we can rewrite that as 5 times 14, and then we want to write that as times x squared again. Well, we have a total of 6 x's. We just wrote down 2 of them, and therefore using exponent notation, we'd have 4 left over, which we could write as x to the 4th power, minus 45 is equal to 5 times 9. Right, and then we have x squared there. All right, so that one, instead of writing it out as a bunch of strings of x's, we can do it a little quicker doing this. And now let's notice our GCF is 5x squared. All right, we have an x squared term in each. We have an x squared factor, I said that incorrectly, in each one of these terms. And we have a 5 factor in each one of these terms. So we can remove that. And when we do, we're left with x to the 7th power plus, okay, this is a 7 on that first x, 14x to the 4th power, and plus 9. And again, we can redistribute that 5x squared back through the parentheses, and it will check and will come back and give us our original result. Okay, so let's look at the next one, and that might be the last one I do in this video, and we'll talk about factoring trinomials in the next video. Turns out this polynomial here cannot be factored. All right, when we talk about numbers that can't be factored, we refer to these as prime. And we use the same terminology for polynomials. We call this a prime polynomial. There's nothing we can take out of both of those terms, and we're going to learn in the next video that that's actually a binomial that we can't factor either. We can factor differences of squares. We cannot factor sums of squares. That can't be broken down at all. We cannot take out any greatest common factor, and furthermore, we're going to see that cannot be factored, period. So that's going to be it for this video. We're going to return with some more in the next video on factoring trinomials.